Hey everybody, I want to finish up the two sample hypothesis testing videos by talking about paired hypothesis testing, which is actually probably the most important one. Um, yeah, probably. Well, we'll see. Let's go to the notes and we can talk about it. So, paired hypothesis testing. The idea here with a paired hypothesis test is the following: if you have two groups and there is a direct connection, not from one group to the other group, but from every member of one group to a single member of the other group. I said that badly. One member of the first group to one member of the second group. A really common connection, for instance, is before and after, right? You want to see if something is effective, so you do you test some characteristic of the first group, and then you do the thing to them, and then you test that characteristic of the second group, or then you test that characteristic of the same group. So each member of the first group is connected directly to another member, or to a member of the second group, specifically themselves. And then the thing that you are testing is what changed before and after, right? So you subtract basically the after group minus the before group to get the thing that you're looking for. And it's that change that we're interested in. So paired hypothesis testing is very specific. You often can't do it because you have to really set it up and do an experiment. You can't do like an observational study. You really have to be doing an experiment where you've got a before and then something happens and then after. And like we're going to see in just a second, my example here is weight loss. The example in the notes is weight loss. Right? We're going to have group before, they go on a diet, group after. The difference in the weights is how effective the weight loss, the weight loss regime was, right? So that's the kind of thing you're looking for with paired hypothesis testing. You can also pair up in other ways. And in fact, this leads to a really interesting phenomenon, which is that for scientific studies, researchers often value having twins, especially in medical studies, because twins are identical twins because they have the same DNA. So it allows allows medical researchers to know that the results they are seeing are not due to some change in genetic makeup, right? It allows them to control for genetic makeup by doing something to one twin and not to the other twin, right? You give one a placebo and one the actual treatment. But anyway, that's the sort of thing that you need to do a paired hypothesis test. It has to be something like that, really specific. You can't just take one group that's kind of related to this other group and test them as groups. What we're going to do instead is we're going to compare one individual to an individual in the other group, specifically subtract the differences in whatever we're measuring, and that's the thing that we're interested in. So from a technical standpoint, this is not really a two sample test. I mean, it is, you have two samples, but what we're actually going to do is the following. So I've written these notes in a weird way. I didn't get a chance to rewrite them before the semester, but basically the example is down here that I want to do. So after all this, I want to do this example here to kind of explain what's going on. And I'm actually going to jump in at B. We're gonna worry about A in just a second. I want to do B first to show you how it works. Then we'll do A afterwards. Like I said, I should have rewritten these. So the idea here is Dr. Henry Valora is conducting a study to see if a particular diet is effective for helping his patients lose weight. He gets 13 volunteers to commit to applying the diet and then measures their weights before they start, and again 8 weeks later after the diet is concluded, and then here's the results, right? So we've got the weights before and then the weights after. So the thing that we really want to do is the following. I want to subtract the weight after minus weights before, right? Because that'll give me total change, where negative would be weight lost and positive would be weight gain. So the thing I want to point out here is I said it's not really a two sample study or a two sample test, because what we're going to do is we're going to do all that subtracting, and then we're going to do a one sample t-test on the differences. So that's the basic idea. So what we have to do is get all the differences first. The way to do that is something in your calculator that I want to show you. So here's whoops, where's my calculator? Why is it? What's going on here? Sorry, computer's been a little weird. calculator is okay. It is up. Good. All right, let's share up the calculator. So here's what I'm going to do. I'm going to type in list 1 and list 2, or I'm going to type in before in list 1 and then after in list 2, and then my differences are going to be list 2 minus list 1. I'm always going to do after minus before. You can do before minus after. It'll work fine mathematically. It just feels a little weird to have like negative values be weight gained to me. It feels like a weight loss should be a negative number and weight gain should be a positive number. And in general, if you do after minus before, that gives you the total change, with negative being a decrease and positive being an increase. So that's the way I like to do it. So I'm going to go to stat and edit, and I'm going to type in the weights into my two lists. And so I'm going to move around my windows a little bit here so I can actually see these things while I'm typing them in. I know you can't see me doing anything, but I am. All right, so list 1 is going to be before, and list 2 is going to be after. So 206, 195, 243, 307, 256, 182, 274, 153. 191, 208. All right. I'll go check to see if I've typed them all in. I've probably got a typo somewhere. I usually do. Let me strongly encourage you to type these in yourself and follow along and not just watch me. It'll actually make it stick better. So, bit of a tangent here. You guys have probably heard of learning styles. Most people have visual learners, audio learners, kinetic. What is it called? Kinetic learners? No, that's not right. But anyway, that's the one I'm interested in. And a lot of people misuse learning styles and think, oh, well, I'm mostly a visual learner, so I should learn things in a visual way. That's actually not right. Learning styles are not meant to be used in that way. What you want to do is combine all of them in as many ways as you can. Like if you can learn something using sight and sound and movement, it will help you remember it better. So it actually helps if you're doing something active, writing things down, typing things into the calculator. All of that will help it stick better, because the more connections your brain has to a thing that you're doing, the easier it is for your brain to retrieve it, or for your mind to retrieve it from your long-term storage in your brain. And so that means that if you're doing something active, those different senses that you're using all help it connect, all help your brain connect to that thing that you did. So that's why moving around, typing stuff will help you remember better. So let me strongly encourage you to type into your calculator while you're watching, or while you're doing this, not just watching. Anyway, let's go make sure I did this right. 200. Yep. Did I actually do this entirely correctly? That might be literally a first. I did. Wow. All right. Great. Okay. So what I'm going to do now is in the header of L3, not in the top entry here, but I'm going to go up into the header of L3, and I'm going to type in the formula for what I want the calculator to do, and I want it to do after minus before. After is an L2 and before is an L1, so I'm going to tell it to do L2 minus L1 in the header here. So L2 is the second function of 2, minus L1 is the second function of 1. Hit enter, and it gives me all the differences there, right? Bunch of weight loss. This guy actually gained 2 pounds, lost 5, lost 11, lost 5, etc. Right? So that is the thing that I want to actually do my hypothesis test on. So what I'm going to do is, let's go write some hypotheses, because we're checking to see if people lost weight while they were on this diet, right? That's the thing I'm looking for. So let's go get a whiteboard going. So my null hypothesis is going to be, well, let's do the alternative first, right? That's going to be easier to write down what it should be. Okay, so my alternative hypothesis is that the difference of the weights after, or the difference of the weights is negative, right? That after is less than before, right? So that my mu before minus mu after is negative. or another way to say that is that mu after is less than mu before. Now, here is where I hate the way your book and every other book I've ever read, or every other intro stats book I've ever read, does this. Wait, did I do that backwards? I did. Pardon me. I apologize. I noticed an error there. Before I go off on this tangent, I got to go fix this. Otherwise, this is just going to bother me, right? It should be after minus before. Not I wrote before minus after when I said after minus before and meant after minus before. So this should be mu A minus mu B. Okay, sorry about that. So here's the thing I hate. The thing I hate is that your book doesn't use this notation. Your book calls this thing mu A minus mu B. They just call it this, mu D. The D stands for difference. And it's not wrong to do this. It is, however, unhelpful because, as I mentioned when we were doing one of the previous videos, this sign right here is the hardest thing to get right. And if you just say mu D, you're not saying what order you're subtracting it, right? So if this is after minus before, then we would want it to be less than 0. If, on the other hand, mu D was before minus after, it could be greater than 0. And the D tells you nothing about that, right? It says nothing about what order you subtracted in, which I hate. So I usually don't write it like this. I will do this most of the time. You can also do, another way you could do it is something like this, mu after minus before is less than 0, something like that. Really, any of these are fine. If you want to use the mu D notation, go ahead. That's what your book does. That's what every book does. And I've never understood why. Like it seems like such a random, easily fixed confusion point that we just have in every book. So anyway, I'm going to do it like this or like this because they both mean the same thing as this. So anyway, there you go. That's what I'm going to do. I've started writing it like this. I'm just going to go ahead and leave it as mu A minus mu B. And let's go ahead and get rid of these things. Erase this guy, erase this. Okay, so there is my alternative hypothesis that mu A minus mu B is less than 0. My null hypothesis then is that mu A and mu B are the same, that the weight loss didn't work, right? The diet didn't work. So mu A minus mu B equals 0. Or you could write that as mu A equals mu B. Right, totally fine. Just the same way we did it before, right? Means the same thing as before. You can write it the same way. I don't know why you wouldn't. So there you go. That's my my null and alternative hypothesis. And so what I'm going to check, so mu A minus mu B, right? This is in L3, right? The differences are in L3. So what I'm going to do is I'm going to do a t-test on L3 to check to see if it is negative. That's it. That's all we're going to do. So let's go back to the hypothesis test, or to the calculator, right? So I'm just going to do a t-test on this column. Let's do that. So stat test t-test, and I actually have raw data here. I don't just have summary statistics. I actually have all the weight losses in the calculator, so I can just use data. I want to do it on, and my mu 0, the mu in the null hypothesis is 0. The list is L3. Frequency list, ignore that, just leave it as 1. And I am checking to see if it was less than. So the alternative hypothesis. So there we go. This is just barely less than 5%, right? So we can reject the null hypothesis with a little bit of, with a little bit of trepidation, right? Because 0.04 is technically less than 0.05, but boy, it's pretty close, right? And so I would really want to do like a bigger study here more than anything else. Now, there's a bunch of complications with this that I want to talk about. And so we will in a second, but for right now, let's just go ahead and write a conclusion. I'm going to go write this on the whiteboard in the same way that I would want to see it on test. So end up with Ttest on differences. P-value about equal to 0.044. So we should reject null hypothesis. Barely. This data suggests the diet works. There you go. Pretty straightforward. Now, thing I mentioned here is that this is the data, which we'll see in just a second, is a little bit problematic. And so I want to introduce to you a new sort of analytical tool called a QQ plot. QQ stands for quantile. It's also called a normal probability plot. So let's go look at our data for a second. I'm going to show you how to make this plot in the calculator. All right, so if I go back to my data, what you might notice is I've got a lot of things around negative something moderate, negative single digits, right? -1, +2, -5, -11, -5, -52. That one appears to be different than the other ones. And if we scroll down a little further, we'll see that is indeed the case, right? We got negative single digits and then a -52, and I guess a -11, but that's, close to single digits. This one's not. So what I want to do is I want to make a normal probability plot. Here's what a normal probability plot does. It does, in kind of a complicated way, what it's going to do is compare the values that you see in L3 here to the ones that you would see if this was actually a normal, if L3 was a sample from a normal distribution. And then it graphs those things. It graphs what the values are versus what you'd expect if they were from a normal distribution. And so what you're looking for is a straight line, essentially. You're looking for some kind of straight line where a steeper line would correspond with I believe, a normal distribution with a smaller standard deviation and a shallower line with a larger standard deviation. But you don't care about any of that. You just care if the line is straight, really. So let's go see what it looks like. So here's how you make a quantile plot. I'm going to quit out of here. And I'm going to go to stat plot, which is the second function of y equals. And I usually leave my QQ plot on plot 3. You can do whatever you want. Now, for me, it doesn't matter because I'm just using VMware, which resets every time I open it up. If you have an actual physical calculator, obviously, whichever one you put it on, it'll stay there until you change it, which is kind of nice. So I usually like to have a scatter plot on plot 1 and a QQ plot on plot 3, but you can do whatever you want. So I'm going to go to L3 or plot 3. I'm going to turn this into a QQ plot, which is the last one. So this is a scatter plot. We're going to talk a lot about this when we get to chapter 13, 12. I think when we get to linear regression. This is also a scatter plot to just connect the dots. You use these for like time series and stuff. This is histogram. We've made these. Your calculator will make histograms. Not that well. It's certainly not as good as sheets, but it will make them. These two are both box plots. Right here's a box plot with no outliers exploded out, and this is one where it finds the outliers using the 2S method, the 2 standard deviation method, and then anything out of more than 2 standard deviations away from the mean is considered an outlier. And then this one is the QQ plot. This is a normal probability plot right here. So that's the one I'm going to select. And so it's going to ask me where the data for this plot is coming from, because it needs to look at, well, okay, what is your actual data? And then what would it look like if it was from a normal distribution? And so this is L3 for us. That's the thing I'm trying to graph, is the graph a probability plot for is the differences. Data axis doesn't make any difference. Mark doesn't make any difference. And then I'm going to quit out of here. Now, you could just turn it on here. I don't like to do that, and I'll show you why. But I'll quit out of here. The reason I don't like to do that is because I always want to go to y equals to see what else is being graphed first. Because normally, if you're like if you have an actual calculator, and then all the stuff you put in your graphs will remain there, and you kind of don't want it there. So I like to come here and look and see what's being graphed first. If I have any equations in here that I want to turn off or delete, and I don't, of course, I have nothing because I just turned on the VMware. But you can turn it on just as easily from here as well. So I'm going to turn plot 3 on, and then I'm going to hit graph, and it's going to show me nothing all that useful because it is zoomed out too far. So what I want to do is I want to use zoom stat, which I think we've used it before. I don't remember if we've used it that much in this class, but we're going to use it a lot more going forward. So this is not actually all the data. I'm going to go to zoom and then hit number 9. So zoom stat is the one I want here. What that does is it takes the thing that you're graphing, whatever the plot is, plot 1, plot 2, or plot 3, or all of them if you have them all on, and it centers up your data so that they are, or it centers the screen so that your data are framed up nicely. All right, this is fairly clearly a significant outlier. And obviously you know which one this is, right? This is the -52. Right, and so what we have here is, it looks kind of like a straight line. It's actually not easy to tell, to be honest, because it's zoomed so weirdly, but this is definitely not following the same line as the other ones. So we have a huge outlier here. We could do the 1.5 IQR test. We could do the Ttest standard deviation test. They're both going to reveal that this is a significant outlier. And I think we can just tell by looking without having to do any math that it's obviously one. So what we have to do is decide whether we want to keep the outlier in or throw it out. And so I'll let you think about that. So I want you to, I'm going to pause for a second. I want you to pause the video and think about, should I keep this outlier in or should I remove it, and why? All right, I'm going to pause. Okay, I hope you're back from pausing the video and thinking. So here's my reasoning about why I would probably want to keep this in, but I'd want to do some more investigating. So a couple reasons. One, the reason I would throw an outlier out in a data set would be if it was gathered in error, for instance. So I think I've used this example before, but when we were originally talking about outliers several chapters ago, but I'll say it again. So here's my example of the perfect time to throw something out. MATLAB gathered data about how many people were logging in on any given day. And I had that data. I'm friends with the women who run the MATLAB. And so I asked for that data so that my students could analyze it and come to some conclusions. And so I'm going through the data, and there's this one day that's very different than the other ones. All the other days are like 180, 210, something in that range, high 100s, low 200s, with the occasional one getting up to like 250. That's the number of people who log in, right? And a 250 day is really busy. That's when the MATLAB's really full. And I got to this one day that was like 93, or some relatively low number, less than 100. I don't remember exactly what the number was. And so I went and asked Allison, the woman who was in charge of the MATLAB, hey, what happened on this day? She said, oh, the logging computer broke around noon and people couldn't log in anymore. So that outlier, that number that was far away from the rest of them, should clearly just be removed, right? If we're trying to analyze how many people go into the MATLAB in a certain day, and this was gathered in error, or this number was not representative of the number of people who went to the MATLAB that day, we should toss it, right? Obvious, pretty easy to tell. It was a measurement error, don't even use it. This was not, as far as we know, right? That guy just lost 52 pounds. Here, let's go look at the data. Here. Right, so that's person number 7 here. He went from 307 to 255. The diet just worked really well for him. And so in that sense, I wouldn't necessarily want to throw it out because it seems to be a real result of the diet, right? The fact that it's unusual doesn't necessarily mean that we don't want to keep it in the study. In fact, in one sense, it's the most important data point in this study, right? Like, wouldn't it be great if this diet worked really well for some class of people? And so I think the right answer to put it in or leave it in or take it out is probably do both, right? We should probably have one kind of analysis if it's in, one analysis when it's out. And if I was presenting this as a research paper, I would want to do both to give as thorough an analysis as possible, because perhaps this particular guy number 7 here, had something about him that caused the diet to work really well, and we should definitely try to identify that, right? If we're trying to, if we've got this diet that we're using, finding particular groups of people who that diet works really well for would be fantastic, because whenever we found a person like that, we could give them this diet and it would work great, right? That'd be great. It would also tell us, well, you're not in that category, so maybe you don't really want that diet, right? Maybe a different diet works better for you because you're not in whatever category we figure out this guy is in, right? It will help us tailor our recommendations if we have a complete analysis and a complete analysis of both methods. Maybe that helps direct further research. So I think we should do both. And so here's how I'm going to do that. I'm going to go back to my calculator. And here's my QQ plot with the point left in. So I'm going to go to my data. So stat and edit. And notice L3 is where I've got these. So I'm going to go to L4. And I'm going to go to the header of L4 and just tell it to make it L3. So I'm going to say make L4 equal to L3. It'll give me the data back. And then I'm just going to go delete this. Delete. There we go. So now I've got the same data, but with that particular guy thrown out. So now what I'm going to do is I'm going to do a QQ plot on L4 to see whether it looks like L4 is from a normal distribution. Oh, by the way, that was the thing I got a bit off on a tangent there. The fact that the line for L3, the QQ plot for L3 was not straight, suggests to us that this was not a normal distribution, or that this was not a random sample from a normal distribution, right? And so let's see if L4 is. All right, so I'm going to go do a QQ plot here. So let's go to stat plot, QQ plot, and we're going to turn the data list to L4. And then we're going to graph this. All right, well, it's still zoomed from the previous time when we had the point over here. So I'm going to go to zoom and zoom stat number 9 again. And that is like the straightest QQ plot you're ever going to see. They're usually not quite this nice. This is indicative of data that definitely looks like it's drawn from a normal distribution, right? So that's what that makes me think, is that the central limit theorem applies just fine to when I throw to the differences when I throw the outlier out. That's not a good reason to throw the outlier out to make your analysis nice and pretty. Don't do that. Don't change your data for that reason. Now, if you go and investigate, like let's say Dr. Valora goes and he talks to this guy who lost all the weight and says, hey, did you just do the diet, or did you do other stuff too to help you lose weight? And if the guy says, no, I just did the diet, it was nothing else, it just worked really well, then great, leave it in. And if he says, I also I tried to exercise more and did some keto as well, okay, then maybe you should throw it out, because maybe he's not representing just the effects of the diet. But anyway, this is the straightest QQ plot you're ever gonna see, right? It's almost a straight line, so that it's basically just a straight line. So that tells me that if this data was from a normal population, or if these differences were from a normal population, this is exactly what we'd expect to see in the results. So I'm entirely comfortable saying that I think the population of differences for before and after in this weight loss study is normally distributed, which is a thing that I would have no way of knowing otherwise. Otherwise, without doing this, right? That's what this is for, is does this population of differences look normal? And it does. Okay, so that here, let's go rerun the test that we did. So t-test on L3. We did this one before. I just want to point something out here. All right, so p-value of 0.044. And x bar negative 7.2. So this is the average difference, or the average weight difference that we see, right? The average person in the study lost 7.23 pounds. So let's go look briefly at the data, because I want to point something out before we run this. So that means that there were 13 people, and if on average they lost 7 pounds, well, 7 times 13 is 91. So that means that a grand total of 91, or it's probably actually 93 pounds, was lost in this entire study, right? Over the 13 people, they lost a grand total of 93 pounds, 52 of which were this one guy. So this one dude has more than half of all the weight lost in the study. In other words, he lost more weight than everyone else combined. So when we rerun this, when we throw him out and rerun the test, do you think the test will more strongly or more weakly detect that the diet works? So again, I'm gonna pause and let you think about that. So pause the video and think about whether you think the test will be more sure that the diet works, or less sure, and what that means about the p-value. So pause the video. All right, I hope you're back from pausing. I hope the conclusion that you came to was that the test should be less sure that weight was lost on this diet, right? We're throwing out most of the weight that was lost. And so when I do a t-test on L4, which is the data, but without the really successful guy, or the guy who lost a lot of weight in it, I would expect that we would have a bigger p-value, right? It's going to be like smaller p-value means we're more sure that the diet works. Bigger p-value means that we're less sure. So my intuition tells me that we should probably, like the other one was really close, so this will probably not be enough information to make us think that the diet works. So let's go ahead and run the test. T-test on L4 this time. Huh. That is entirely different from everything I just said, right? Our p-value before was 4.4%, and now it's 0.7%. It's way smaller. Why would that be? So the way we can interpret this is that we are significantly more sure that the diet works, that people actually lost weight over this 8-week period than we were before. Isn't that weird? So again, I'm going to ask you one more time to pause the video and think about why the heck that happened. And let me encourage you to run a t-test on L3, run a t-test on L4, look at everything you see on the screen, and see if you can figure out why we're more sure now. All right, so pause the video. Okay, I hope you're back from pausing. Here's why we can be more sure now. Look at the standard deviation. The sample standard deviation here is 4.2 pounds. If we do t-test on L3, I think the standard deviation was about 14. Yeah, it's about 14. So having that one crazy outlier in the data makes the standard deviation so much bigger. The p-value actually gets smaller when we remove it, even though it accounts for most of the weight loss. So that's just a kind of unexpected result. But that's one of the things that throwing out outliers does, is it makes your data nicer, right? Our data is a lot nicer when we don't have the one number that's way different than all the others that we have to try and explain. And so the test, like when you get outliers like that, it makes your test much less certain. And so throwing out outliers often makes the analysis much cleaner, which is not a reason to throw them out, right? The world is messy. And if you're trying to explain the world with math, right, you're trying to explain some real world phenomenon, don't throw out the messy stuff, because you're missing the real world part then. Or at least that's not to say don't ever throw out outliers. That's just saying don't use that as a reason to throw out outliers. Gotta keep the messy stuff in there if it's appropriate to do so. So that's why the standard deviation goes down so much when we take it out, that everything just works nicer. So Ttest on L4. I did L1. Let's try that again. L4. There we go. Makes us more certain that weight is actually being lost because there's so much less variance in the results, right? The results are all about the same, and so we're pretty convinced that that's the real deal, right? The diet probably makes you lose, or probably helps you lose, about 3.5 pounds on average. So that's QQ plots. You want to use a QQ plot or a normal probability plot anytime you are trying to determine if a set of data could reasonably come from a normal population. Now, why would you want to do that? You want to do that if you're trying to use the central limit theorem and you don't have enough data points. Like that's when it's really important to do a quantile plot, is to check to see if your data is normal, the most common use of which is to determine if the central limit theorem applies or not. Yeah, so that's the thing I wanted to say about that. So let me go back to the notes here, see if we can get an answer going to these questions, right? So make a normal probability plot. We certainly did. To see if the assumption the population of differences is normally distributed is reasonable. And the answer is not if we have this outlier in here, but yes, if we don't, right? So having this outlier in here makes our analysis much more messy. Now, that doesn't mean that we should just immediately throw out everything we said on this whiteboard, right? It doesn't immediately invalidate this conclusion. But what I really should say is something like this. This data suggests the diet works, but the results were a little bit irregular, right? With this outlier in, we do get under the 5%, but it's really not. It's not totally clear that this is really nice. So with the outlier removed, let's say this, with the outlier removed, we get a p-value of 0.007, making us more confident of the diet's effectiveness. More study is warranted to determine if patient number 7's results can be replicated for other patients. By other patients. That is the sort of answer that will get you extra credit points on a test, right? This is what I would say, I don't know about thorough, but more thorough discussion of the results than I'm insisting upon to get 100%, right? Like if what you said was something like, well, with the outlier in, we had 0.044 p-value, and with the outlier out, we had a 0.007 p-value, making us want to reject the null hypothesis in either case, and therefore we think the diet works. I would give that answer 100%. This one is better than that. This answer not only says, here's what the data means, but also where I think we should go with this if we're actually doing a study. And so something like this, will receive an extra point or two on the test if you can be this thorough and this detailed and actually give a reasonable discussion of what the data means. And ultimately, that's really what I want you to get out of this class more than anything else. Do you understand what the test is telling you? Or like, do you understand what the numbers mean? Do you understand what that means you should do, right? What are the consequences of seeing numbers like this? And if you do, then great. That is precisely what I want. More than anything else is for you to be able to confidently answer a question like this with solid reasoning, right? That's really what I want. Can you use these numbers, the numbers that you're seeing, to help you understand the world and explain it, especially in a way that anybody could understand, right? If you read something like this, or making us more confident of the diet's effectiveness, you don't have to know what a p-value is in order to understand from this statement and the previous one that our statistical analysis suggests this diet works, and it might work better for some kinds of people that we haven't determined yet, right? You could figure that out without having to understand even what a p-value is at all. And that's what I want a good conclusion to be like. I want a good conclusion to be able to help someone who does not know statistics to understand the results anyway. And I think that is probably a good place to end on. Let me pop back to the notes for a second. I had asked you to make an confidence interval for the mean amount of weight someone can expect to lose by following this diet. Well, that's easy enough. If you do this stat, test, and t-interval, you have to ask yourself, I should really probably make two confidence intervals, one for one with the outlier in and one with it out. So we might as well just do that just to kind of remind you of that. I like to throw in these questions now and again, even though the confidence interval is not really part of the hypothesis test, but you can certainly do it. It's not hard at all, right? We remember how to do this: stat, test, t-test, or t-interval, number 8. And then you can do one on L3 or on L4. And we actually have data here, so I'm just going to do it on L4, 95%. So we are 95% confident that the mean weight with the outlier removed falls between, or the population mean weight would fall between, or mean weight loss would fall between 6.2 pounds lost and about 0.8 pounds lost, right? So we're 95% confident that the mean weight lost falls in that range. You could also do this with the outlier left in by doing it on L3. And remember, the standard deviation is going to be a lot larger here, so this should be a much wider interval. And it is, right? Negative 15.72 up to 1.26. So a thing you might say is, wait a minute, 0 is in that interval. If 0 is a reasonable value for mu, why did we reject the null hypothesis before? And the answer is that 95% confidence interval doesn't actually go with this hypothesis test that we were doing because it's two-sided. or excuse me, because this interval is two-sided, but the hypothesis test was one-sided. So let me draw a quick picture and show you what I mean. So let's go over here. Let's make a new whiteboard. So here is what we did. We had an alpha of 5%, but our alternative hypothesis was just to the left. Right, so what we had was something that looked like this, where this is 5%. Right, and so our alpha was this region over here. Our alpha was this percentage. When we did a confidence interval, we did a 95% confidence interval, but it's two-sided. So what that means is that our range of values is such that outside of the confidence interval, oh, this shoot. Sorry. Outside of the confidence interval, there's 2.5% on either side. And this is one of those rare cases where the difference between this and this mattered. Like what I'm trying to say here, our mean difference fell in this region here between the 2.5 and the 5%. So that's why there's this little range in here that's mismatching. So if you want to correct this, what you can do when you're making your confidence interval is make your confidence interval so that it's if it's got a one-sided alpha of 5%, just make your confidence interval 90% instead of 95%. So you'll have 5% over here and 5% over here, and you'll have a perfect match of the of rejecting the null hypothesis, always going with having the hypothesized mu fall outside the confidence interval. So I'm going to go ahead and go back to the calculator. I'm going to make a 90% confidence interval just to show you that that's what happens here, right? So this is barely on the inside. Oh, I drew it on the wrong side, didn't I? Whatever. That 0 is barely in this interval, and if I go and make a t interval with the data from L3, but I make a 90% confidence interval, it won't stretch over 0. See, just barely. And this 0 being just barely outside the interval corresponds with the p-value being just barely less than 0.05. Those things go together. So that's what happens. That's why there was a mismatch, and why if you have a one-sided hypothesis test, you basically double the alpha in order to make the confidence interval match up with the hypothesis test. So you can do that in this case, and it works out fine. Okay, that actually is all I want to say about two-sample hypothesis testing. So let's go back very briefly to the notes. Where are they? There we go. And so we learned how to do 4 things essentially. One, combine normal distributions, right? We learned how to that was, oh, I didn't put that in the summary, but that was this stuff where we were where we just had 2 normal distributions, and we learned what the distribution of the differences was if we subtracted those 2 normal distributions from each other. And then we learned how to do, Then we learned how to do a 2-sample t-test, or 2 independent sample, I should say, comparing 2 independent means. T-test, right, where we did this, where we found out what the sampling distribution of all possible differences from samples from 2 different all the possible differences of means from 2 different samples. That's what I'm trying to say there. If those original distributions were normally distributed, you end up with this, which I never showed us how to calculate this statistic, but it's like this in general. I expect that you will use the 2-sample t-test on your calculator. I won't ask you to do this, but if you want to see how the test statistic is calculated, there it is. And it's, by the way, I should point out, this is exactly the same as exactly the same method as we did before, in the sense that we've got x bar minus mu divided by the standard error. It's just we calculate those things differently, right? X bar is now the difference of the x bars, mu is the difference of the mu's, and the way we calculate the standard error is different than the way it's not just S over root n anymore, now it's this combined way. So same idea, different formula. But again, I'm going to expect you to use 2-sample t-test on your calculator. That's the thing I want you to know. Make sure you can interpret properly and you know what everything means. And then 2-proportion t-test, same thing as same idea. We've got 2 proportions are different from each other, testing to see if 2 proportions are different from each other using this distribution. And then paired t-tests, which I'm going to put everything in here, but it's really a 1-sample t-test on the differences, right? So you find the difference in the results and then do a 1-sample t-test on those differences. Now, that does mean that it has to make logical sense for you to subtract the results, right? From one group, you're going to subtract one person in the second group. And then you're going to subtract off one person in the first group. Boy, I said that awkwardly. Sorry. You're going to take one person in the second group and you're going to subtract off the corresponding person in the first group. That means that there must be that correspondence to connect the two, because otherwise it doesn't make any sense to be subtracting them. So that's the thing you got to watch out for. For a paired test, it's really, you're testing the differences rather than the individuals themselves. So finding those differences has to make some sort of logical sense. Otherwise, you shouldn't do it. You should do an independent samples t-test, which is that first one that we covered. Okay, I think with that, I want to go ahead and end the video. So let's go ahead and stop sharing. I'll just say, yeah, I do want to end the video there. So I'm going to do that, and I will see you guys in the next one.